Hello, and welcome back to another IB Math speedrun with me, Vince. This is the final speedrun of today, and we're going to be talking about higher order derivatives. So yeah, let's jump right in. So, we've already met our friend. If we have like a function, then its first derivative, actually, let's use the function notation for this. If we have a function, then we can get its derivative. But this is actually only the first order derivative because, if we step past this, we can actually get a derivative of the derivative, which we call the second order derivative. And so, since multiple dashes, we can go to the third order and then fourth order and fifth order and then sixth order, and we can go on and on and on. And, writing out like multiple dashes, like something like this would be bad at best. So for higher order derivatives above the third derivative, we use the notation f and then just put the number in the brackets here and then put x. So this will mean the seventh derivative of the function. And there is one formula that may help us a teensy bit here, and it's called Leibniz's formula. And so what that states is if we have a function f of x that's made up of two functions, so we can use the product rule. If we want to get the first derivative, this will be equal to uv prime plus vu prime. And if we get the second order derivative, what we can actually get, if you expand this, is uv double prime plus 2u prime v prime plus vu double prime. And it goes on and on and on. So it actually looks like a binomial expansion, sort of, which is extremely interesting, but I guess, yeah, that would be correct. So that's one handy trick we can use when getting very high order derivatives. Okay, so now let's move on to some questions. So the first question is, well, I guess I'll do the even ones. So if f of x is equal to 3x to the 5 minus 2x squared plus 1, find f to the 4 of x. And, well, we can actually cheat a little bit here because we know that, okay, let's try. Actually, no, we don't need to derive all the terms because we know, first of all, after one derivative, this one term will no longer exist. After three derivatives, this negative 2x squared term will no longer exist. Since it is an integer it's a positive integer. If the power of x is a positive integer, eventually it will get removed from the derivative. And so after four derivatives, the only term remaining will be 3x to the 5. So let's just find the fourth derivative of 3x to the 5. So the first derivative is equal to 15x to the 4. The second one is equal to 60x to the 3. The third one is equal to 180x squared. And so finally, the fourth one will be equal to 360x. So the fourth derivative of this function will be equal to 360x. So yeah, that's cool. Now on to the next one. So we have the function f of x is equal to x to the 4 over 12 minus 2x squared plus 5x plus 1. We need to find the values of x for which f double prime x is equal to 0. So which the second derivative is equal to 0. So first let's find what the second derivative is in the first place. So if we get the second derivative of this function, well, the first derivative will be equal to 1/3 x cubed minus 4x squared plus 5, and the second derivative will be equal to x squared minus 8x. So we need to find values for which this is equal to 0. Actually, wait, no, this is just 4x. X squared minus 8, my bad. So we need to find values for which this is equal to 0, and this is pretty obvious. This is just going to be x is equal to plus or minus the 2 square root 2, which is square root 8, and this will be the answer, so that's when the second derivative will be equal to 0. Yeah. Okay. Let us, after I find the question we're on, hold on. Oh, sorry, this would be x squared minus 4. Oopsies. All right. And so this would actually just be plus or minus 2. Ignore the 2 square root 2, it's just plus or minus 2. So yeah, that one was also pretty simple. So now we can move on to the next one. And that would be if we're given f of x is equal to x to the 4 plus px squared plus qx plus r, and this passes through the point -1, 16, and at this point the second derivative is equal to the negative of the first derivative, and that's equal to 16. And so we need to find p, q, and r. Okay, so it passes through the point -1, 16. So what do we know from that? Let's gather all the facts first. So first let's this is going to be it's going to be a set of 3 linear equations. So first let's substitute 16 is equal to x to the 4, so that's 1 plus p minus q plus r. So we have one of the equations. And let's get the first derivative of this. That would be equal to x cubed, 4x cubed. Oh my gosh, what was that? 4x cubed plus 2px plus q. This is the first derivative. And so we know that at this point, this is equal to -16. So we get that -16 is equal to 4x cubed, so -4, plus 2px, so that's minus 2p, since x is -1 at this point, plus q. Finally, we get the second derivative, f double prime x. This will be equal to 12x squared plus 2p. Yeah. And so at this point, of course, x being -1, we have 16 is equal to 12 plus 2p. Yep. Well, what can we tell from this information? We can tell p immediately is equal to 2. And then here, 16 is -4 minus 2p plus q, so q must be equal to -8. And finally, 16 is 1 plus p minus q plus r. 16 is 1 minus 6, so that's -5 plus r. So r must be equal to 21. Is that correct? 1 minus 6, 5. Yeah, so that should be correct. Or not. What in the world are they giving me? Sorry, let's go through this again. I think I've made a mistake somewhere. X to the 4 plus px squared plus qx plus r. passes through the point -1, 16. Okay, the first derivative is equal to -16. That's 4x cubed plus 2x squared, 2px plus q. And the second derivative is equal to 12x squared plus 2p. And that's equal to 16. So 12x squared plus 2p equals 16. So 12 times, well, I don't think the mark seems correct, honestly. You know what? Let's graph it. So if you're unsure about anything, I would always just graph it, because why not? So we have x to the 4 plus 2x squared plus qx. What did we say q was? Q is equal to -8, I believe. Minus 8x plus 21. And at the point -1, well, let's just check. At the point -1, it should be equal to 16. Okay, so yeah, we do have a problem. It's probably my fault, because at the point -1, this equation is clearly not equal to 16. So let's go back here. At the point -1, this would be 16 is equal to 1 plus p plus q, minus q plus r. Okay. So we had p is equal to 2, q. Hello, I'm back. And so what I figured out is that I was being silly, and this is actually minus q, which should be -8. So this r value should actually be, well, 16 minus 1 minus 8 minus 2 is equal to r. So that's equal to 5. So r should only be equal to 5. And if we plug it into a graph over here, which I've constructed, if we set r is equal to 5, we can see that the function is equal to 16 and -1, and the second derivative is equal to 16, and the first derivative is equal to -16 at 1. So this satisfies it. Simple mistake. So, on to the final question of today. And the final question is, given f of x is equal to 1 over x, so f of x is equal to 1 over x, find the first 5 derivatives and conjecture an expression for f to the n of x. So find the first 5 derivatives. Okay, so let's rewrite this as x to the -1. And we get f prime, the first derivative is equal to -x to -2. The second derivative is equal to 2x to the -3. The third derivative is equal to x is equal to 3x to the 6x, should I say, to the -4. And you can do the fourth and fifth derivatives by yourself, but I think it's unnecessary. Sorry, this is -6x to the -4. And so we need to conjecture an expression for f to the n of x. So what I would say is that, honestly, this would probably be equal to -1 to the n, first of all, times x to the -n plus 1. Since third derivative is equal to 6x to the -4 already, all multiplied by n choose, let me just look, 1, 2, 6, what do we know about that? 1, 1, 2, 1, 1, 3311461. It's equal to just factorial, so times n factorial. Oh, so it's probably equal. Sorry, not n choose r, but simply just n factorial will do the trick. So I would conjecture that this is equal to, if I can get the pen out, that would be helpful, yes. -1 to the n. Come on. Negative. Oh, it's really slow. I think I might have to swap software at this point. It's crashed. Hold up, I'll be back. Sorry, my whiteboard just crashed, but I'm back. So we have -1 to the n times n factorial times, or I mean, I guess all over, no, I'll just use times x to the n plus 1, or x to the -n minus 1. And let's prove this for the base case. First of all, base case of n equals 1. We have -1 to the 1, so -1 times 1 factorial, which is 1, times x to the -1 minus 1. So we have -1x minus 2, which is equal to -x to the minus 2. And I think that should be correct. Yes, so for the first derivative, we have this. Now we have to do the inductive step. So assuming this is true, let's prove it for the next one. So therefore, f of n plus 1 is equal to -1, hold up, f of n plus 1 x. We want to prove this is equal to -1 to the n plus 1 times n plus 1 factorial times x to the -n minus 2, I guess. Yeah. So let's prove it now. So, I mean, this is pretty simple. We have to bring this down over here, and we have to get the derivative of this number. So let's get the derivative in parts. So this would be equal to -1 to the n, because that's a constant, times n factorial, which is also a constant, times, well, what's x to the -n minus, what's the derivative of this number? And the answer would be -n minus 1 times x to the -n minus 2. And, well, we know this is equal to, we can rewrite this as -1 times n plus 1. And this allows us to rewrite this all as -1 to the n plus 1 times n plus 1 factorial. Since n factorial times n plus 1 is equal to n plus 1 factorial times x to the -n minus 2. Since left-hand side is equal to right-hand side, well, we've proved it by induction. And so, yeah, that will be it for today. So I hope you enjoyed the speedrun, and I hope you learned a lot more about higher order derivatives and just, differentiation in general. See you in the next one.